You're welcome. You're welcome. Well, come to think of it, kid, honestly, I could go on and on. I could explain every natural phenomenon. The tides, the grass, the ground. That was Maui just messing around. I killed an eel, buried its guts, sprouted a tree. Now you got coconuts. What's the lesson? What is the takeaway? Don't mess with Maui while he's on the breakaway. All right. I'm teaching to no one here. Nobody's here except for me. That's okay. It happens sometimes. But now I will sing songs because no one is here to stop me now. Today's the 16th, all right. I'm working on getting the lyrics down to You're Welcome from Moana. Almost there. I think I pretty much got down Shiny, which is also a very good song. You guys are really gonna make me teach to no one and nothing. That's fine. Just fine. Right, no one else is on Zoom, right? I'm just not like saying crazy things and people are there. I mean, yeah, no, I'm just me, myself, and I. All right, let's see. Yeah, we'll do a couple graphs and then we will do some optimization. So I saw in class that he gave you a slant asymptote problem. So let's start with that. So let's graph. What have I got here? Sure, we'll start with this one and then I'll make another one. F of x equal to x cubed over x squared minus 1. Now, the way you can tell that you're going to have a slant asymptote is if the degree on top, which is 3, is exactly 1 larger than the degree on the bottom, which is 2 here. So if the highest power on the top is 1 larger than the highest power on the bottom, you're going to have a slant asymptote. Well, let's find out the usual things. So first off, I would start by finding the intercepts. So intercepts. But I can start numbering things too. It's good to number things. So intercepts, usual deal. For the y-intercept, we set x equal to 0. You get f of 0 equal to 0 over 0 minus 1, which is 0. So 0, 0 is your y-intercept. It's also going to be your x-intercept. You set y equal to 0. You're going to set x cubed over x squared minus 1 equal to 0. And that's just going to lead you to x equal to 0. Not very exciting. Oh, well. The next thing we do is we find the asymptotes. So we're going to find the vertical asymptote by setting the denominator equal to 0. So you're going to set x squared minus 1 equal to 0. I personally would choose to factor this. The reason I like factoring this, well, I'll say in a moment here. When you factor this, you can see that each of your vertical asymptotes, x equal to 1 and x equal to -1, come from factors that have odd powers. Now, we kind of get this information from the first derivative, but it's also true that if you do this here, you know that if the power that if the vertical asymptote came from a factor with an odd power, you're going to have an opposite direction kind of. So one side is going to go up to infinity, one side is going to go down to negative infinity. All right, let's talk about. So there is no horizontal asymptote in a rational function. If the degree on top is larger than the degree on the bottom, you don't get a horizontal asymptote. But again, if it's exactly 1 larger than the degree on the bottom, you do get a slant asymptote. So there's no horizontal asymptote here, but there is a slant asymptote. And the way you find the slant asymptote, also called an oblique, is by doing the polynomial division. So x squared, sure, plus 0x minus 1 divided into x cubed plus 0x squared plus 0x plus 0. Probably don't need all that, but it's good to write all the terms. So let's see, you multiply x squared by x, take it x cubed. Oh, yay, there's someone there. Barry, it's just you and me so far. There's no one in the classroom yet. That's okay though.
Okay, sounds good.
I was just starting an example. I was doing a graphing example. So let me just recap what I've done so far. So I started with, oops, sorry, I keep doing that. All right. I started with this function here, x cubed over x squared minus 1. And before anything, I noted that we know that we're going to have a slant asymptote for this example because the degree on top is exactly, welcome, come on in, 1 larger than the degree on the bottom. I was just talking to someone who's going on Zoom as well. Remind me of your name. Rachel. Rachel, we're just talking about this graphing example here. And I was pointing out that we know we're going to have a slant asymptote because this rational function The degree on top is 3, which is exactly 1 larger than the degree on the bottom, which is 2. We found the intercepts, which were not that hard. We found the vertical asymptote by setting. I just remembered I had to check. I forgot to check the thing you asked me about. We found the vertical asymptote by setting the denominator equal to 0, and we were just about to find the slant asymptote by doing the polynomial division. So if you divide the top by the bottom, you kind of have to fill in the extra terms here. You multiply x squared by x to get x cubed. X times 0x is 0x squared. X times -1 is a minus x. We subtract x cubed minus x cubed is 0. 0x squared minus 0x squared is 0. And 0x minus x is x plus 0. And you could keep going here, but I mean, there isn't really any, well, actually, you can't keep going here. This term here has a smaller degree than the divisor there, so we can't continue the division. So what we know is that this quotient up here, that's your slant asymptote. So your slant asymptote is the line y equals x. Cool. And that's always how you find the slant asymptote. If your rational function has a degree on top that is 1 larger than the degree on the bottom, then you know you're going to have a slant asymptote and you do this division. We'll do another example as well after this. So that's the usual stuff, and then we're going to find the first derivative stuff. So first derivative stuff. And again, if there's questions about anything I've said that you missed, feel free to ask. I'm happy to revisit it. So let's take the first derivative. Okay, so f prime of x is going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the denominator squared. All right, let's see what we've got here. So multiply. So this is again the case where you really do have to simplify this so you can see where your critical values are going to be. So simplifying this, I'm going to have 3x to the 4th minus 3x squared minus 2x to the 4th, all over x squared minus 1 squared. And simplifying that a little bit further, 3x to the 4th minus 2x to the 4th is x to the 4th minus 3x squared, all over x squared minus 1 squared. Finally, factoring out an x squared from the top, x squared times x squared minus 3 over x squared minus 1 squared. And if you set that equal to 0, you're going to get 3 solutions. You're going to get, really, I'm just setting the top equal to 0. So I'm going to get x equal to 0. And if I set x squared minus 3 equal to 0, I'm going to get x squared equal to 3, or x equal to plus or minus the square root of 3. And then technically, we also have plus or minus 1 as our pseudo-critical values, right? They're not actual critical values because they're where we have vertical asymptotes, but we need to include them when we do the number line for the first derivative. Okay, so let's draw a little number line here. I think we've got enough room here. 0, 1, -1, root 3, -root 3. Come on in. We're just talking about an example graphing. We're graphing x cubed over x minus 1. We found the intercepts. We found the vertical asymptotes. We found the slant asymptote by doing the polynomial division, because we saw that the degree on top was 1 bigger than the degree on the bottom, which means we're going to have a slant asymptote. We take the derivative, is kind of gross, and now we've just found the critical points, which are plus or minus root 3, plus or minus 0, and plus or minus 1, but not really, because those are the pseudo ones where we have vertical asymptotes. So here's what I would say. To be a critical value, a real critical value, the value has to be in the domain of the original function. And if you look at the original function here, plus or minus 1 are not in the domain. The other way of thinking about it is we know we have vertical asymptotes at plus or minus 1. And it's like, oh yeah, I can't have a maximum or a minimum there because it's undefined there. All right, so now I would start way right of root 3 and plug in something like, I don't know, 4. 4 squared is positive, 4 squared minus 3 is positive, 4 squared minus 1 is positive, the whole thing's positive. And if I was doing this efficiently, I would point out my denominator is always going to be positive here. I'm not even going to think about plugging into the denominator because I do not have to. It's always positive because it's squared. So if I pick something between 1 and √3, so here's what I would do. I don't really want to look for a number because it's not easy. Pick something just a tiny bit, like in your mind, pick 1.1. Okay, 1.1 squared is positive. 1.1 squared minus 3 is definitely negative because 1.1 squared is smaller than 3. It's like 1.21. And then the bottom's always positive. So positive, negative, positive. The whole thing is negative. All right, between 0 and 1, 1/2, positive, negative, positive. Between 0 and -1, -1/2. Okay, so this is where the whole plugging in thing becomes a little bit tedious. Alternatively, we could have factored this more. Now, you might not love this, but I want to point out you could have factored this as x squared, and you can factor x squared minus 3 as x minus √3 times x plus √3. It's not wrong. It's not typical. And then the bottom you could factor as x minus 1 times x plus 1 squared, or x minus 1 squared times x plus 1 squared. So now if you do the whole thing where you look at the powers, you can see, okay, well, when I cross √3, √3 came from there, odd power, change the sign. 1 came from there, even power, sign stays the same. 0 came from there, even power, sign stays the same. -1 came from there, even power, sign stays the same. Negative √3 came from there, odd power, sign changes. It's usually a faster way of doing it if factoring it all out is not too tedious. Or you can plug in a number in all of the 1, 2, 3, 4, 5, 6 different intervals here, which is kind of a pain in the butt. So what does that tell us about our function? It tells us that it is going up and then down and then down and then down and then down and then up. Do we have any relative extrema? Yeah. What do we have? Well, where could we have a relative extrema? And also positive square root of 3. And not at -1. Well, definitely not at -1 because they're not even real critical values, but also not at 0 because it's down on the left and down on the right. So we have a relative maximum at x equal to the negative square root of 3. We have a relative minimum at x equal to the positive square root of 3. Should I find the y values? Probably. I don't really want to because I know they're going to be gross. If I plug it in, f of negative square root of 3 is going to be the negative square root of 3 cubed. Ugh. Divided by 3 minus 1. And the same deal here. You plug that one in, it's going to be the positive √3 cubed over 2. Oh, do we need to find the second derivative? It's always a question. Do you really need to find the second? Yeah, I mean, if you're being asked to graph it and they've said you need to find the concavity / the inflection points, yeah, you really have to find the second derivative, which is a terrible mess here. Yeah, we should do it. It's good practice. All right, so here's our first derivative. And I definitely, even though I've done a bunch of factoring here, usually the unfactored form is the better place to take the derivative from. I don't want to have to use the product rule when I do the derivative at the top here. So I'm going to use that piece instead. So my first derivative is x to the 4th minus 3x squared over x squared minus 1 squared. And now I'm going to find the second derivative, which is probably not going to be very nice. Oh, well, that's life sometimes. So let's do it. Bottom. Derivative of the top is going to be 4x cubed minus 6x. I feel like I didn't say those words. They're minus 6x. I feel like I just kind of whispered them. And then top times the derivative of the bottom. I have to use the chain rule. It's going to be 2 times our stuff to the first times the derivative of the inside stuff, all divided by x squared minus 1 squared squared. That's the problem with these quotient ones, is usually all the work here for the second derivative gets pretty gross. but it's not impossible. So we're going to factor out an x squared minus 1. Yeah, sure. We'll factor out an x squared minus 1. And then we're left with an x squared minus 1 times the 4x cubed minus 6x minus an x to the 4th minus 3x squared times a 2 times a 2x. All divided by x squared minus 1 to the 4th. One of those cancels with one of those. Again, I'll make the observation that when you do this derivative, you started off with x squared minus 1 squared. You took the derivative, you got x squared minus 1 to the 4th in the bottom. But then after you simplify, that power there should just end up being 1 larger than that power there. Always works out that way if you simplify. Okay, now for the gross part, we have to actually multiply this out. So we get 4x to the 5th minus 4x cubed minus 6x cubed plus 6x minus 4x times these things are minus 4x to the 5th minus is plus 12x cubed. Good Lord. Who came up with this question? These cancel. And then 12x cubed minus 6x cubed minus 4x cubed is 10. So 12 minus 10 is 2x cubed plus 6x all over x squared minus 1. Holy smokes. All right. So factoring out the 2x from the top. This one always feels a little bit disappointing because you do all this work. And what do you get? You get 0. You set this equal to 0. Your only real solution is x equal to 0. And then, of course, your pseudo solutions plus or minus 1. If you set this part equal to 0, you don't get anything because x squared plus 3 is always bigger than or equal to 3. Questions about anything I did there? Okay. Oh, I guess we should do the second derivative sign chart. I thought I was going to have enough room on this piece of paper for my graph as well, but I guess not. 0, 1. I really feel like, so one thing I would point out, I could have made a mistake here. I don't think I did, but I could have. There are useful tools for taking derivatives. Like there's like, I remember when I was a student, the Wolfram differentiator and later on integrator are great places you can go type in a function and then it'll show you what the derivative is. So if you're not sure about your work you've done, there are many places you can go check your work. And I think Tab also posted something recently about like some other tool for taking derivatives. So definitely, if you're doing something complicated and you want to check it before you spend time graphing the thing, check your work. It's not a crime. It's totally fine. So yeah. All right. So second derivative. If I pick something larger than 1, like 2, positive, positive, positive. If I pick something between 0 and 1, like 1/2, positive, positive, negative, and the negative thing cubed stays negative. And then it's going to change signs because the 0 came from the x, which is to an odd power. And it's going to change signs again because the negative 1 came from the x minus or x plus 1 that's in here to an odd power. Or you could, again, keep checking numbers. So it's concave down, concave up, concave down, concave up. All right. Show me on your fingers, how many inflection points do I have? I have inflection point at 0. Why don't I have one at -1 or at 1? Right, because they don't exist there. I was a little confused. I was expecting to see either 1s or 3s, but I saw a couple 2s, and I was like, how are they getting 2? So, right, we can't have inflection points there, but normally you would get an inflection point anywhere the concavity changed. So it changes from here to here. So there would have been one there, but it's not defined there. It changes from here to here. Oh, we get one there. It changes from here to here. We would have gotten one there, but again, undefined. And I really like when I draw my number lines to draw in the vertical asymptotes. I really think that's a really good reminder of the fact that, oh yeah, we have a vertical asymptote there. Notice it was important graphically to include these pseudo-critical values because the sign of the second derivative did actually change from the left of -1 to the right of -1, and from the left of 1 to the right of 1. So we actually really do need to include those points on our number line. even though they're not actually critical values. All right, you've done all the work. Now we just have to throw it all on the graph. Okay, so, all right. So graphing it all. Let's see, I've got my intercept of 0, 0. My vertical asymptotes at +1 and -1. And then I don't have any horizontal asymptote, but I do have a slant asymptote. The slant asymptote was the line y equals x. So you're just going to draw the line y equals x, except you're going to draw it dashed because it's an asymptote. You're going to try and draw a straight line. Wow, that's oof. It's rough. That's a straight line there. Yeah, okay. And then what else do we have? And then the most important piece of information, probably the sign chart. So of the first derivative, this chart right here is really what's telling me how things are looking. So I know my graph is, oh, and I guess I should plot that's the other thing I forgot, my critical value. So I had when I plug in -√3, I was getting -√3 cubed over 2. Is that a positive number or a negative number? -√3, if you cube it, is it positive or negative? Still negative. And then divided by 2, still negative. So -√3 cubed over 2 should be a negative number. So we have some sort of -√3, which is between -1 and -2. Maybe it's like right about there. Some negative number. Maybe it's right about there. That's supposed to be a relative maximum. It's meaning I should be doing something like that. Okay, right? Because we're going to be increasing and then decreasing. So we're going to do this. I'm sorry, I can't quite see that. Right? I was increasing and then I got decreasing. And then to the right, still decreasing. So we're going to be decreasing from -1 to 0. And then from 0 to 1, sorry, I'm trying to show you all the things at once here. From 0 to 1, still decreasing. And from 1 to √3, still decreasing. Did I do something stupid? I might have done something stupid. Sorry. I'm trying to show you the right thing here. So I plotted a point that was probably not in the right spot. There's no good reason I should have crossed this slant asymptote. Not that you can't cross the slant asymptote. It is totally fine to cross the slant asymptote. But you shouldn't be crossing it without like the need to cross it. Like I did here, right? I had to cross the slant asymptote there because of the way the function was going. But the way this probably should have actually looked is more like this. It probably should have been something like down here. Probably did something more like that. That's how it probably should have actually looked. So how do you know to do that? I don't know. It's a good question. Practice. Yeah. Yeah. I mean, if you really wanted to, no, yeah, I don't love that. You could actually like plot the point, but like find the value so that you know whether or not you're above this line y equals x or not. I know that we're below it looking at the numbers, but like they're not nice numbers, so it's kind of hard to tell. And then just to say a few more things about this, when we graph this, right, as you move way away from the middle, so like when we're coming down here and then bottoming out at our relative minimum, √3 comma √3 cubed over 2. After that, we're increasing, but we also have to get closer and closer and closer to the slant asymptote. Just like it was a horizontal asymptote, you have to get closer and closer to it as you move way, way to the left or way, way to the right. But yeah, I'll draw a better one when I post the notes so that it actually looks right, but that's how it should have looked. So not this part here. Terrible. I know I feel bad doing this, but this part here is how it should have actually looked. Kind of ugly. Okay. Any questions?
So, horizontal, sorry,
Slant asymptote.
Is that really only to like help us know where like why can you cross it?
Why can you cross a horizontal asymptote? Good question. Let's take a look. So the thing is, so here's what a horizontal or slant asymptote mean. They mean as x gets really, really big, the function gets close to this other function. So actually, let's go back for a second and look at the polynomial division, because that's actually where kind of the magic is occurring, or the information is happening. So we look at the slant, if we look at the polynomial division we did to get the slant asymptote, we did this. We did that. We were finding x cubed divided by x squared minus 1. And we did that, and we did, I'm just going to do the lazy way. Multiply x by x squared. You get x cubed minus x. We subtract, and you're left with just an x. Since that power there is less than that power there, we're done. But you can write this in a different way, right? So just like when you do actual division, like for example, if you did, sure, let's say you did 47 divided by 6. 6 is into 47, what, 7 times? Sounds right. 7 times 6 is 42. 7 minus 2, 47 minus 42 is 5. So when you write 47 divided by 6, you can really write it as the quotient 7 plus the remainder 5 divided by the divisor 6. That's kind of where mixed fractions come from. 7 and 5/6 is the same as 47/6. The same idea holds here. You can rewrite this division as the quotient. And I'm going to show you another way of getting there in a second. Plus the remainder, which is unfortunate that they're exactly the same, but oh well, that's what we've got, divided by the divisor. Let me show you a little bit more work to get there, because I think it's worth seeing. I could, sure. I could rewrite this top part as x cubed minus x plus x. Everyone okay with that? And then I could break these up into 2 pieces. That's x cubed minus x over x squared minus 1 plus x over x squared minus 1. And then I can factor out an x from the top here. And then the x squared minus 1s cancel. And then we get exactly the same thing. Just to make it more clear as to why we're getting what we're getting. And you might ask, why wouldn't you do it this way every time? Because, well, it's not easy to do it that way every time. I just happen to notice that it worked easily this time. But usually the actual polynomial division is the story here. Okay, so why are we saying this? Well, because what we're saying is this function, x cubed over x squared minus 1, is equal to this function, x plus x over x squared minus 1. And now what happens as x gets really, really big? Well, yes, I know it gets infinitely large, but very specifically, this part gets really, really small, right? The power on top is smaller than the power on the bottom. And if you did like the limit is x goes to infinity of this and did division by x squared of everything, that would go to 0. So the point is, as x goes to infinity, the function x cubed over x squared minus 1, or I should say y equal to x cubed over x squared minus 1, becomes very close to the function y equals x. That's why we're saying that's our slant asymptote, because as x gets very, very large, the function we have just starts to look like the line y equals x. If you zoom way out, you kind of just see the line, and the stuff in the middle means kind of nothing. But in the middle, anything can happen. You can cross your slant asymptote bajillions of times if you really wanted to. But the slant asymptote isn't talking about what's happening in the middle. It's talking about what happens as you move way, way, way to the left or way, way, way to the right. That's kind of the whole idea there. So yes, long story short, you can cross the horizontal asymptote. You can cross a slant asymptote. They're not barriers the way a vertical asymptote is, which you can't really cross unless someone really, really tries hard to make it so you can, which is annoying. But you can make up weird piecewise functions where you cross a vertical asymptote. Super annoying, but whatever. Okay. I think that's good. All right. Should we do another one with the slant asymptote? I think we should. You guys are like, no, you have no choice. We're gonna do another one. Okay. No, okay. So let's see here. Let's do this one. Let's say we have, let's see, 1 second here. Yeah, I want that. Okay, let's say we have f of x equal to x squared minus 2x, yeah, over x plus 1. Do I like this choice? I think I like this choice. Okay, let's find all the usual things. So the first usual thing, y-intercept, set x equal to 0. You're going to get y equal to f of 0, which we can see is going to be 0. You get 0 minus 0 over 1. X-intercept, set the function equal to 0. So you're going to set x squared minus 2x over x plus 1 equal to 0. But we know that when we're setting a rational function equal to 0, we're really just setting the top equal to 0. And we factor out an x. So we get x times x minus 2 equals 0, which means our x-intercepts are both 0, 0, and 2, 0. Or x equals 0 and x equals 2. Again, today, this room just feels icy. I feel like I'm standing right under a vent or something. I mean, it's fine. It's chilly. Okay. Intercepts, then the asymptotes. You might do things in a different order. My personal order is always this: first intercepts, then asymptotes, then the first derivative, then the second derivative. That's the usual way to go, I think. So asymptotes, and I always do the vertical asymptote first because it's usually less work, to be honest. You're going to set the denominator equal to 0, and you're going to very easily get x equal to -1. Do you make sure you write the x equal to if it's a vertical asymptote, or the y equal to if it's a horizontal asymptote, or the y equal to x plus 2 or whatever if it's a slant asymptote? Again, there is no horizontal asymptote because the degree on top is greater than the degree on the bottom. But there is a slant asymptote because the degree on top is exactly 1 larger than the degree on the bottom. Which makes sense if you think about it, right? When we do the polynomial division, if the degree on top is 1 larger, then the quotient is always going to be a line, just something times x plus a constant. Let's do the division. Polynomial division. So x plus 1 divided into x squared minus 2x. You multiply x by x to get x squared, and then you multiply it out, you get x squared plus x. We subtract negative 2x, or sorry, x squared minus x squared is 0. Negative 2x minus x is negative 3x. Some people do the thing where they like change the signs of the second part. That's totally fine. This is not the way I ever like to write it. And then you bring down the next thing. So we should have written a plus 0 here. It's not super important, but it's kind of nice. And then you repeat the process. What do you multiply by x to get negative 3x? Oh, negative 3. And you do it, you get negative 3. Really, I should say, I should stop right there. I shouldn't even do it. I shouldn't even write this here. Once you've got the whatever times x plus or minus the constant over there, that's the end of the story. Y equals that is your slant asymptote. You could finish the division if you really, really want to. Negative 3 times x is negative 3x. Negative 3 times 1 is minus 3. And then subtract. And you get 3. But you don't need to finish it. Our slant asymptote is y equal to x minus 3. All right. Now for the fun part, all the derivative things. So we're going to find the first derivative things. I don't feel like you're usually being asked to find the intervals where it's increasing or decreasing, right? We kind of just look and see what those look like. But if you are asked to write them down, you should practice writing them down. Maybe we'll do that. First derivative things. Okay, so quotient rule, lots of quotient rules for these. The bottom times the derivative of the top, which is 2x minus 2, minus the top, times the derivative of the bottom, which is just 1, divided by the denominator squared. And then we have to simplify this to be able to find the critical values. So yeah, multiplying out the top, we're going to get 2x squared minus 2x plus 2x minus 2. And then distributing the minus sign here, minus x squared plus 2x. All divided by x plus 1 squared. And then let's see. You can cancel a few things here. The negative 2x and the positive 2x cancel. And you get 2x squared minus x squared is just x squared. And then I've dealt with those. And then I've got a plus 2x. This is not, good job, James. All right, well, what happens when you make up problems? 2x squared, yeah, plus 2x, minus 2. All right, fine. Bummer. Oh, well. So set this equal to 0. And we set the top equal to 0. I have some bad news. It doesn't factor. And if a quadratic doesn't factor, how do we solve it? Everyone's favorite formula, the quadratic formula. Yes, we have to use the quadratic. That's not true. You could do it a different way. There's like this whole thing with completing the square. Nobody wants to do it that way. We should just use the quadratic formula, even though it's not going to be pretty. So we're going to get x equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So here are our critical points. Negative 2 plus or minus the square root of 4 plus 8 is 12 all over 2. I am going to simplify this. Negative 2. The square root of 12 is the square root of 4 times 3. Or the square root of 4 times the square root of 3, which is really 2 times the square root of 3. So we get, divided by 2. And then each part gets divided by 2. So we really have negative 1 plus or minus the square root of 3. I feel like I've done this example before and this turned out nicer. Oh, well. Maybe I switched the sign somewhere that I didn't mean to. Just let me double check my work again here. Let me double check just to make sure I didn't do anything really stupid here, but I'm pretty sure this is right. 2x squared minus 2x plus 2x minus 2. Nope, that seems totally correct. How disappointing. Yeah. All right. So those are critical points. So let's put them all on the number line. What else? So critical points here. So I've got negative 1 plus root 3 and negative 1 minus root 3. And also I should include negative 1 because I have a vertical asymptote there. That makes the derivative undefined. So negative 1 and then negative 1 plus root 3 and negative 1 minus root 3. Okay. So when we do this, well, let's just pick a number bigger than negative 1 plus root 3, which is easy to do. You know why it's easy to do? You can pick as big a number as you want. Pick 1,000, which feels kind of silly, but like pick 1,000. 1,000 squared is really big. Plus 2,000 minus 2, really big number on top. Definitely positive on the bottom. Okay, now here's the harder part. In between negative 1 and negative 1 plus root 3, yeah, I don't love it. I mean, I think 0 is in there, but it might not be easy for us to mentally like just see that eat fast. So here's the thing I would remind you of. We just solved a quadratic equation equal to 0, and we found 2 solutions, which means that if you could have factored this, it would have factored as x minus one of those solutions to the first power times x minus the other solution to the first power, which means each of those solutions come from factors with odd powers, which means the sign has to change. That's always going to be true if you found 2 solutions from a quadratic equation, right? It's kind of like saying you wanted to solve x squared minus 5x minus 6 equal to 0, and instead of factoring it, you did the quadratic formula. If you did the quadratic formula, you would end up getting eventually x equal to 6 and negative 1, which means we could have factored this as x minus 6 times x plus 1. But they have to be to the first power. There is no other choice. So whenever your quadratic formula gives you 2 solutions, we know that those solutions each came from factors with a degree of 1, which means the sign has to change there. The negative 1, the sign is going to not change because that negative 1 came from a factor with an even power. And then we're going to change again. It's a little dicey. It's not dicey. It's just so much. It's a little bit more sophisticated, maybe. All right. So now we know that our function is increasing, then decreasing, then decreasing, then increasing. So we have a relative maximum at x equal to -1 minus root 3. I would not find the y value here. Relative minimum at x equal to -1 plus root 3. All right. Even though things are ugly here, it is good practice. In fact, it's probably even better practice because things are so kind of gnarly. So let's find our second derivative. Let's remind ourselves of what our first derivative was. First derivative was x squared minus 2x. Oh my gosh, papers. X squared plus 2x minus 2 over x plus 1 squared. You all should you should try to find the second derivative faster than me. I'm going to write a little slow here. I'm going to give you a head start. Start finding the second derivative. There's what I got. I got x plus 1 squared times the derivative of the top, which is 2x plus 2, minus the top, which is x squared plus 2x minus 2, times the derivative of the bottom, which was 2 times x plus 1 to the first times 1, but we didn't write that because we didn't need to write that. All divided by the denominator squared, which is x plus 1 to the 4th. And then I'm going to factor out an x plus 1. I'm also going to factor out a 2 because I see that right there, there's actually a 2 I can factor out. So instead of factoring out this x plus 1, I'm actually going to factor out this 2 times x plus 1 just because it's already kind of there nicely for me. It doesn't matter which one you decide to factor out. They're the same. So I'm going to rewrite this as 2 times x plus 1. I'm factoring this out. I'm factoring this out. I'm left with an x plus 1 squared minus, and let's distribute the minus sign, x squared minus 2x plus 2 divided by x plus 1 to the 4th. Cancel an x plus 1 and an x plus 1. Simplify. That 2 hangs out. X plus 1 squared is x squared plus 2x plus 1 minus x squared minus 2x plus 2, all divided by x plus 1 cubed. And then we cancel the x squareds, we cancel the 2 x's, and we end up getting 2 times 1 plus 2 is 3 over x plus 1 cubed, or 6 over x plus 1 cubed. Which feels kind of like a lot of work for a relatively weird, not weird, simple answer. So what's the only point we're going to put on the number line for our second derivative? Everybody. What's the only value we're getting? If we set this either equal to 0 or undefined, what's the only number we're getting? Almost.
-1.
Thank you. Yeah. But we know it's not going to be an inflection point because it was already a vertical asymptote. Now we still want it because we want to know about the concavity of our graph. So if we look at our graph, if we pick something bigger than -1, like 2, the whole thing's positive. And if we pick something less than -1, like -3, the whole thing's going to be negative. So it's definitely concave down, concave up, but we do not have an inflection point because we have a vertical asymptote there. All right. Question? Okay, you looked like you had a question. Sorry. Let's try graphing this thing. Putting it all together. Sorry. All right, let's go back and look at what we had. So we had a y-intercept of 0. We had x-intercepts at both 0 and +2. And we have a vertical asymptote at -1. And then we also had some critical points at, oh yeah, they were gross. So it is worth knowing a few irrational numbers approximately. I would encourage you all to remember that the square root of 2 is about 1.4 and the square root of 3 is about 1.73. Square root of 3 comes up often enough that it's good to have an idea of about where it lives. So if I do -1 plus the square root of 3, it's going to be plus about 1.7. So it's going to be like maybe right about there. And then -1 minus the square root of 3 is going to send me 1.7 to the left. So maybe right about there. And then I didn't find the y values because I was being lazy. So, well, we'll deal with that in a second. So let's look at our sign chart here. Our sign chart looks like that. So we are increasing and then decreasing and then decreasing and then increasing. Now, I'll remind you, you can only cross the x-axis where you, I forgot to draw something important. What did I forget to draw? The slant asymptote, which was y equal to x minus 3. So that's going to be 1, 2, 3, 1, 2. Just for clarity here. So y equals x minus 3 has a y-intercept of -3 and an x-intercept of +3. So I'm drawing my slant asymptote through those 2 points. Okay. Sorry. Sometimes you need a lot of room on these graphs to make sure things are in the right place. So the reason I make terrible noises like this is I probably need to actually plug in -1 plus √3 and -1 minus √3 to see what my y values are. But I'm pretty sure it's going to be something like down here. And the reason I'm pretty sure that is because my graph is increasing from -infinity up to -1 minus √3. Relative max, decreasing afterwards. And then on the other side of -1, just again, here's the sign chart again, right? I was increasing, decreasing, and now after -1, I'm still decreasing. I got to hit my intercept there. That's where my relative minimum is going to be. And then increasing afterwards. Got to go through that intercept as well. And then keep getting larger and larger and larger. So a reminder, you can only cross the x-axis if you have an x-intercept. Otherwise, you can't. And then you have to follow the pattern of your sign chart for your first derivative. Again, this is definitely maybe, I wouldn't say anomalous because I've made it up and after. Obviously, I make up lots of problems that have terrible values. But usually if you're reading something like this, the numbers would probably end up being a little bit nicer and you'd actually be able to plug in. Like if you plug in to the original function, so our original function was x squared minus 2x over x plus 1. And if you try plugging in something like x equal to -1 minus √3, it's not impossible, but it's not pretty. Yeah, it's really not. Yeah, I really don't want to. You don't want to either, I'm sure. But I'll probably, I don't know. I'm not sure. That's what it's going to look like, though. And again, no, I don't think I have anything else to say. Increasing, decreasing. Oh, yeah. Concave down, concave up, as our sign chart would indicate. Often, you can kind of graph the graph without doing any of the concavity stuff until after you've already graphed it. Like, I think we could have pretty easily graphed this if we'd known the values of our max and min by just saying, oh, yeah, increasing, decreasing, decreasing, increasing. We have these intercepts, we have these asymptotes. You can usually get a pretty good idea of what the graph looks like without the second derivative information. Yeah. How much time have we got? We should start talking about optimization. I would love to do one more example, but we should start talking about optimization. So Optimization. To me, optimization feels similar in process to related rates problems, in that you're going to be given a word problem and you're going to have to read the words and then interpret stuff and come up with a couple of equations to use to then do the process. Just like with the related rates, you had to kind of figure out what was changing and then write an equation relating those things and then take the derivative of both sides and figure out what to do. So there's a lot of interpretation, critical and reading skills that are involved in these optimization problems. You have to be a careful reader. Let's look at kind of what's considered a fairly typical first example. Let's say, sure. This is problem 3. A cattle rancher plans to enclose a rectangular pasture next to a river. Oh yeah, we'll do it this way. Yeah. If 180,000 square feet of grass is, I don't know, required to feed the herd, and assuming cattle don't like to swim, meaning right, the river is a border that we're not going to build the fence on. That's why there's a river there or a barn there or a thing there that we don't have to build. That we're being smart. What dimensions of the pasture will minimize the amount of fence needed? Okay, so whenever I'm doing one of these problems, whether it's related rates or optimization, I almost always want to draw a picture. So here's my river that we're not going to build the fence on. And then over here, next to the river, we're going to fence in some rectangular pasture. And just like with related rates problems where we labeled the things that we didn't know, or we labeled the things that were changing in related rates problem, here we're going to label the things we don't know. I don't know how long that side should be, so I'm going to call that X. I don't know how long that side should be. I'm going to call that Y. I don't know how long this side should be. What should I call it? I should call it X because it's the same length as that side. So things that are the same length, you should give the same name. You don't want to use more variables than we need to. All right. So for optimization problems, you typically have to come up with 2 equations. That's not exactly the right word. You have to come up with the thing you want to optimize and an equation for the constraint. So what are we trying to maximize or minimize here? Good question. What are we trying to maximize or minimize? What dimensions will minimize the amount of fence needed? Okay, so we need an equation for the amount of fence. So the amount of fence is going to be the length of X plus the length of X plus the length of Y. So the amount of fence is going to be 2X plus Y. Notice that it is not equal to a number because we don't know the value for it. That's what we're trying to find. So typically when you do this, you're going to write something like either, I don't know, like you write fence is equal to 2X plus 2Y. And we're trying to minimize that function. But I really want to stress here, we never set this equal to a number because we don't know what it's equal to. So that's what we're trying to optimize. And then there's some constraint or some limiting piece of information. Here we are limited by the fact that we want the area to have 180,000 square feet. So we want to have 180,000 square feet. Well, great. I know how to find the area of a rectangle. It's length times width. So our constraint equation is that X times Y has to equal 180,000. Notice that this equation has something equal to a number. And that is pretty standard when you're finding a constraint. So you've got the thing you want to optimize and the limiting piece of information, the constraint. After that, the process is there's like steps that are always kind of the same. The steps are take your constraint, isolate one of the variables. And then whichever one you've isolated, plug that into the other thing that you want to optimize so that you have a function of one variable. Because usually the problem here is that, right, this fence equation, there's two variables there. And we don't know how to find the maximum or minimum of a function of two variables. But we definitely have spent a fair amount of time finding the maxima and minima of functions of just one variable. So that's what we're going to do. So take your pick. Usually, you should try to make the choice that's going to make life easier for yourself. I think it's pretty similar here, so I'm going to solve for y. So y is going to be 180,000 divided by x, or if you prefer, 180,000 times x to the negative first. And then we're going to substitute that in for the y in our equation right there. So now our fence equation as a function of just x is going to be 2x plus 180,000 times x to the negative first. And now we're going to do the usual thing. We're going to take the derivative and we're going to set it equal to 0 to hopefully minimize this function. Now, we will need to check to see that it actually is a minimum, because when you find critical values, it could be a max or a min. So we're going to take our derivative. It's going to be 2 minus 180,000 x to the negative second. And we're going to set that equal to 0. And then we're going to solve for x. So I'm going to try and make the math a little easier on myself here. I'm going to rewrite this as 2 equal to 180,000, but instead of times x to the negative second, I'm going to write divided by x squared. And then I'm going to multiply both sides by x squared and divide both sides. I'm essentially going to switch the 2 and the x squared. Right? Multiply both sides by x squared, divide both sides by 2. So you end up getting x squared equal to 180,000 divided by 2, which is 90,000. So x is going to be, technically I should write plus or minus the square root, but would it make sense for x to be a negative number when it's the length of this, one of the sides of this pen? No. So definitely in these optimization problems, you should also think about kind of the, what's the right word here? The domain that makes sense for your function, right? X shouldn't be able to be 0 or negative here. So we need x to be just the square root of 180,000 divided by 2 is 90,000. And I think the square root of 90,000 is 300. All right. Typically at this point, there are two things you have to do. You have to read the question again to figure out what they are. So the question says, and usually there's one or two things the question can say. It'll either ask you like, what are the dimensions that will minimize the area or minimize the fence, or how much fence will you need that is minimum? Here they're asking for the dimensions, meaning they're asking for x and y. But they could have just as easily asked for how much fence will you actually use to make this pen, which would have been then whatever x, 2x plus y was equal to. So just be careful when you're reading the question. You want to make sure you answer what they're asking for. We'll look at that a little bit more. Yeah, we got time. So here, yeah, let's go ahead and write it here. So we know that x needs to equal 300 feet. And then I can find out what y is because we almost always have an equation for what y is in terms of x. So if x is 300, then y is going to equal 180,000 divided by 300. Or 18,000 divided by 30, or 1,800 divided by 3, which is 600. So y is going to be 600 feet. And usually you can get away with just saying that's your answer. But technically, we should be checking to make sure that that actually is a minimum. Right? Maybe it's a maximum. Maybe we did bad math and we maxed it. We used all the fence we possibly could to make this stupid pen. So usually you check by using the first derivative test. Actually, yeah, This is where you usually check by using the second derivative test. So let's actually do it that way, because I think it is more standard. And I was so close to using just one piece of paper. So is x equal to 300 actually minimizing f of x equal to 2x plus 180,000 x to the negative first? Well, let's do the second derivative test. So the second so our first derivative was 2 minus 180,000 x to the negative 2. And our second derivative is going to be 0 minus 2, so plus 2 times 180,000 times x to the negative third. Or I would probably write it as 360,000 over x cubed. And then what do? We plug in our critical value. Now here's a tip. You don't need to actually know what you get when you plug it in. You just have to know if it's positive or negative. So if I plug in, what was it, 300? I'm going to get 360,000 over 300 cubed, which is obviously positive or negative. Which is obviously positive. Okay, if the second derivative is positive, which way are we concave? Are we concave up or are we concave down? Up. So if your second derivative is positive, oh my gosh, the words. If your second derivative is positive, your function is concave up, which means, do you have a minimum or a maximum? It's got to be a minimum. So yay, we're happy, right? We see that x equal to 300 does in fact minimize our function. It's a fairly standard thing to have to do to check to see if you actually get the thing you're looking for. Now, most of the time, if people ask you to find the thing that does the thing, they're not going to try and trick you and make it so it's only the other thing, right? If you're being asked to minimize something and you only get one critical value, that's going to be the thing that minimizes it. Now, occasionally some functions you'll have more than one critical value, and then you will actually have to test to see which one does give you the maximum or the minimum you're looking for. Okay. Questions before we do another one? Another one? Yeah, we got time for another one. All right. Just in case anyone's curious about attendance, I've been a little bit lazy. I haven't updated the attendance since maybe like Monday, so sorry. I'll try to get to that today. I've just been a little busy. All right, let's look at another optimization problem. Sure. Yeah, which one should we do? Yeah, let's do that one. A cylindrical can. A cylindrical can is to be made to hold 20 pi cubic inches of volume. The material for the top and bottom costs $1 per square inch. And the material for the sides, or for the side, I guess, right? There aren't multiple. It's one side. It's the whole round part. For the side costs, where'd it go there? 80 cents per square inch. Find the minimum cost of the cylinder. All right, so cylinder. Draw ourselves a cylinder. I personally like to try to start with the function I'm trying to maximize or minimize, but people often find it easier to start by writing what the constraint is, and we can totally do that. So we are constrained by the fact that this cylinder has to hold a volume of 20 pi cubic inches. So we should label, sorry, I'm getting ahead of myself here. We should label some sides. There's your height. There's your radius. And the equation for the volume of a cylinder is pi r squared times height, or the base area of the circle times the height of the thing. And we need that to be equal to 20 pi. That's our constraint, that the volume of the cylinder is equal to 20 pi. And certainly it looks to me that when we use this constraint, I'm going to solve for h, because I don't want to have to square root both sides when I'm solving for r. So usually one thing looks easier to solve for. Most of the time, that's the right choice to make. I'm going to isolate h here by dividing both sides by pi r squared. In fact, let's go ahead and do that now. We're going to get h equal to 20 pi divided by pi r squared, and the pi's will cancel. So we get h equal to 20 over r squared, or if we prefer 20 times r to the negative 2. Either one of those might be what we use. But we kind of got ahead of ourselves here. I normally would have started out by looking at the thing I actually want to maximize or minimize. And so the thing is, we're not just minimizing the surface area here, we're minimizing the cost of the surfaces. So the surface area of a cylinder is the following. The surface area is the top circle area, which is pi r squared, plus the bottom circle area, which is also pi r squared, so you get 2 of those. And then the around part, which I'll remind you is 2 pi r h. Again, what I'm thinking about there is I'm thinking about like this being a roll of paper towels. If I unroll that paper towel, it goes all the way around. It's just a rectangle. It's a rectangle whose height is h and whose length is the circumference of the circle, which is 2 pi r. Seem good? Seem good. Okay. So then, but that's not my thing I want to maximize or minimize. I want to minimize the cost. And the problem is the top and the bottom have a different cost than the side part. The top and the bottom cost $1 per square inch. So I'm going to multiply how much area they are by the $1. So it's going to be $1 times 2 pi r squared. And the around part costs 80 cents per square inch. So I'm going to multiply the area of the around part by 80 cents. And then I'm going to dispose of the dollar signs. I'm going to write the dollar signs. So the cost here is going to be 2 pi r squared plus 0.8 times 2 is 1.6 pi r h. And certainly it looks to me from this thing I'm trying to minimize, that it's definitely the right call to solve for h over here, right? Solving for h, I don't have to plug in right there. Whereas if I tried to solve for r, first of all, I'd have square roots, and second of all, I'd have to plug it in there and there. So it's usually, well, I mean, it's good to just look and see what seems like the best thing to solve for. So now we're going to plug in. So our new cost equation is going to be 2 pi r squared plus 1.6 times pi times r times h, which is 20 r to the negative second. That is our h value, our h equation. And we should definitely simplify this before we start taking the derivative. Be careful if you're like me, if you write your times as dots, make sure that 1.6 doesn't look like 1 times 6. Let's do a little bit of simplification. When I write this, I do like to write c as a function of r. It lets me know, oh yeah, I'm writing c is just a function of the radius. And it's going to be 2 pi r squared. 1.6 times 2 is 3.2. So 1.6 times 20 should be 32. So 32 pi, and then r times r to the negative second is r to the negative first. And now we're ready to find the critical points here. So we're going to take our derivative. It's going to be equal to 4 pi r minus 32 pi r to the negative second. So something I've learned about myself over the years doing these kinds of problems is I definitely prefer to write my powers as negative exponents when I'm taking the derivative. But then once I've taken the derivative and set it equal to 0 to solve it, I like to bring everything to where they're positive exponents. So I would much rather write this as 4 pi r minus 32 pi over r squared equal to 0. And you can do this a couple different ways. You could factor out if you really wanted to. I would probably just bring one thing over to the other side and say 4 pi r equals 32 pi over r squared, and then multiply both sides by r squared, so that 4 pi times r squared equals 32 pi, and then divide both sides by 4 pi and get r cubed equal to 32 pi over 4 pi, which is just 8, and the cube root of 8 is 2. That worked out really nice. 2 inches. All right, so here's my usual go-to. After I've done all this work to find my critical value, then I go back and read the question again and figure out what they're asking me to actually find. So if I go back and read the question again, the question said, a cylindrical can is to be made to hold 20 pi cubic inches of volume. The materials for the top and bottom cost $1 per square inch and 80 cents per square inch. Find the minimum cost of the cylinder. So if I just wanted to find the minimum cost, which is all they're asking me to do, I could just go back and plug in r equals 2 to the cost equation and be done with it. So we're not just going to do that, but we could and say, well, C of 2 is 2 pi times 2 squared plus 32 pi. I'm going to write divided by 2 instead of times 2 to the negative first, which is going to be 4 times 2 is 8 pi plus 16 pi. So the cost is 24 pi dollars, which I know is a funny number of dollars, but okay. Somewhere between 73 and $80. I don't know exactly. Probably smaller. But really, normally people are going to ask you for the dimensions, right? I tried to make this different just to point out that you might get asked for the maximum or minimum value instead of the dimensions. But normally we would ask for the dimensions. Say, okay, the dimensions would have been, well, we found r equal to 2 inches. And the height is, well, here's the thing about the dimensions. Once you know the first one, you should somewhere already have the other dimension as a function of the thing you just found, right? We solved for h to be able to write the thing as a function of one variable. So somewhere in all the work we've done, we should have h equal to something with just r's in it. And we do. It's right there. H equals 20 over r squared. So h equals 20 over r squared. And if we plug in 2, h is going to be 20 over 2 squared, which is 20 divided by 4, which is 5. So h equals 5 inches. Those are the dimensions that we think minimize this, but we didn't actually check to see if it was a minimum. And yeah, I really actually, like just in the last hour, become a lot more of a fan of using the second derivative. I just think it's sometimes easier. We'll talk about other ways of seeing if it's a max or min as well, because there are other ways. But if we just want to take this and see if it's a max or a minimum, let's do the, so take this r equals 2 and see if it gives us a maximum or a minimum. Let's go ahead and check the second derivative test. We've got our first derivative right there. Our second derivative is going to be 4 pi. Minus 2 times minus 32 is plus 64 pi r to the negative third. And so if we plug in r equal to 2, c double prime of 2 is 4 pi. Well, it doesn't even matter, right? I mean, it doesn't, okay, it doesn't not matter, but I don't really need to think that hard about what's going to happen here. Because if I plug in 2, I get 64 pi divided by 2 to the third. And regardless, I'm adding stuff here. So the whole thing's definitely going to be negative or positive. For sure positive. Second derivative positive, concave up, which means you have to have a minimum. So we definitely, yes, r equals 2 does minimize C of r. I can't imagine Tab hasn't said something about checking to see if things are maxes or mins. Or that if he hasn't yet, that he won't, because it's something, it's pretty standard practice. So you have to check. Now on an exam, so how much time I've got? The last thing I'll say today is that let's say you had a discussion on an exam and you had little time. This is the only critical value you found, and you were supposed to check to see if it was a minimum. Well, great. So here's the work I would do if I was trying to fake it. Like, hey, well, I know it needs to be a minimum, so I know the second derivative needs to be positive. So I would say, okay, great. C double prime of 2 is positive. Check. Without actually doing the work. Or you can use the first derivative test and say, so here's the cheater way to do the first derivative test. Throw 2 on your number line. You know it needs to be a minimum. So you know it needs to be decreasing and then increasing. Yeah, I definitely plugged those numbers into the derivative and checked to see that it was negative over here and positive here. Didn't you see me do it? I definitely did it. But I didn't really. But I know it was going to be a minimum because that's the only number I got. And they said find where it's minimized. No one's asking you to find where it's minimized and then you're only having a maximum. So it's a little, I mean, it's not cheating. It's just using all the knowledge you have to make smart decisions. The one thing I'll say about this, we didn't talk about this a lot today. If you're trying to do this using the first derivative test, you typically do have a limited domain. Technically, if you look at your original function over here, this is 2 pi r squared plus 32 pi divided by r. R can't be 0. R can't be negative. So really, we should have started this at 0. So that's kind of the endpoint of our domain. And R can be as big as you want it to be, actually. You could have a really, really big, you could have a really dumb looking cylinder that looked like a pancake, right? That was very, very wide and very, very short, that would still have the necessary volume and cost a lot because you made it too big. All right. If you're going for a set volume, you can have really weird dimensions as long as nothing is 0. You can make it really, really tall and skinny, or really, really wide and flat. But to minimize the cost, you want to make it neither of those things, because otherwise then you're just getting really, really big dimensions in one way.